Hello viewers, welcome back. So in the previous video we have introduced you to what exactly theory of computation is and what are its various applications. We had also started with the very first topic, that is introduction to finite automata. Today I'm going to continue from where we had left off in the previous video. I'm going to start discussing what are the various concepts and basic definitions involved in this particular chapter of finite automata. Then we will take up some basic problems, and then we will keep on moving ahead in this beautiful world of theory of computation. So without wasting much time, let's get started. Welcome back viewers. So let's start this particular video by discussing the agenda, that is what are we actually going to learn in this video. Well, in the previous video we had seen what exactly is a finite automata. We had seen a very basic problem on finite automata. So in this video let's discuss certain concepts related to finite automata, and then we'll start straight away with the problems. So the very first thing is what exactly is an alphabet. As we know, right now I'm writing something in the English alphabet. So as we all know, there are 26 letters in the English alphabet. A similar kind of a concept applies over here in the world of theory of computation. We will learn what exactly is an alphabet, and then following it up with what exactly is a word or a string. So initially there will be an alphabet. For example, if I talk about binary numbers or binary alphabets, they could be written something like this: a set of 0 and 1, where this symbol is nothing but a sigma symbol, or we can say this is nothing but an alphabet, right? In the world of theory of computation, this is how we write or denote an alphabet. Similarly, when we combine those alphabets to form something meaningful, then it is termed as a string. For example, I can create a string of length 2 using only binary numbers. So I have these many possible combinations. I can have the string as 0 0, I can have the string as 0 1, I can have it as 1 0 and 1 1. As I have already mentioned the condition that it should have a length 2, so these four are the only options that is possible, right? Similarly, when we move ahead, we'll form something called as a language. Now what is a language? Now in the previous example, I said that this is a string, this is a string, this is again a string, and this is again a string. So when we combine these strings together, we form a language. For example, L is nothing but a set of 0 0, 0 1, 1 0 and 1 1. So this is nothing but, I can say that L is a language which consists of all the possible combinations of binary numbers of length 2. Is it making sense now? So this is how we are going to gradually move ahead up in the ladder of theory of computation. So I have these set of definitions ready for you. You can simply write it down. These are my handwritten notes. So I will drop a link in the description section. You can go over there and download these handwritten notes. So first of all, what is an alphabet? As I had discussed just now, let me now define it in a more formal way. What exactly is an alphabet? An alphabet, sigma, is defined as the finite set of input symbols. As we are talking about finite automata, now what exactly is finite automata? Finite automata is nothing but, we call it as FA, or in its simplest form we can call it as FSM. So what is finite automata? Finite automata is basically a collection, or we can say it is a combination of inputs which are finite in length. For example, over here you can see it is a set of 0, 1 and 2. I have nowhere written it as 0, 1, 2 dot 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 dot, because I have finite number of inputs. Based on those inputs, I can create an automata. So that is what we call as a finite automata in its simplest sense. Because if I have infinite number of inputs, I won't be able to converge to a solution. That is where finite automata comes into picture. So if we are given a finite sequence of inputs and we need to design a machine based on that, that is where finite automata comes into picture. Clear? So according to this example, an alphabet is defined as the finite set of input symbols. For example, 0, 1 and 2, where 0, 1 and 2 are symbols or letters. So whenever I say alphabet, alphabet is nothing but combination of these symbols, where 0, 1, these are nothing but symbols or letters. Fine. So a combination of these symbols is what we call as an alphabet. So I hope this is making sense. Fine. So let's go ahead and let's take the second definition. The second definition is what we call as strings. A string or a sentence or a word is nothing but defined as the finite sequence of symbols over the given alphabet, which we have already discussed. It's nothing but a finite sequence of symbols over the given alphabet. We have already seen 0, 0, 0, 1, 1, 0, and 1, 1. What are these? These are nothing but some finite set of symbols which are in a particular order. As you can see, I have written 1, 0. I have also written 0, 1. They are two distinct values. They are not same because the sequence matters, right? So similarly over here, in the example, 0, 1, 2, 0, 1, 0, 2, 1, 2, etc. These are certain sequences of symbols derived from the given alphabet. That is 0, 1, and 2. Fine. So that is what strings or sentences or words mean in theory of computation. Next up, we are having a definition called as string length. Now, what do we mean by string length? It is very simple. Let's assume this particular string x is equal to 2120. Now, what is 2120? It is nothing but it might have been obtained from a particular alphabet which consists of 0, comma 1, comma 2, right? So now we have created this particular string from these alphabets 0, 1, and 2. So I have got this as 2120. So what should be the length of this particular string? You can pause this video for a second or two and just let me know what will be the length of this particular string. This particular symbol is nothing but the length. The parallel bars is nothing but the length. So what should be the length of this? Is it going to be 4? Is it going to be 3? What should be the answer? What is the answer? Kindly let me know in the comment section. Fine. So let me go ahead. The answer is going to be 4, irrespective of repeating symbols. Now many of you might have answered as 3 because 2 is repeating over here twice. But it doesn't matter because it is a particular sequence. As I have already mentioned, 1, 0 is not same as 0, 1. So over here 2120 is not going to be equal as 0 to 1, 0, right? Obviously they are going to be different numbers, different symbols, because both are having some unique value. So that is why 2120 is going to be the string and the length of it is going to be 4 and not 3. So I hope it is making sense. Similarly, let's go ahead and see the next definition, basic definition, that is empty string. This is a very important concept not only for this lecture but also from the point of view of getting the fundamentals of the subject clear, right? So what exactly is an empty string? Empty string actually hota kya hai? Let's see. Empty string is nothing but the string of length 0 would be called as an empty string denoted by this symbol. Now what exactly is the string of length 0? Now whenever we are saying string of length 0, I can say it like this. It is a set with 0 values or 0 elements inside it. If I say a set consisting of this, I can say that its length is 1. If I say there is a set where the characters are like this, AA, AB, BA and BB, I will say that this is a string of length 2. So in the same fashion, if the set doesn't have any characters inside it, it is termed as an empty string or a string of length 0. It is denoted by this symbol called as epsilon. Fine. So I hope that makes sense. Now you must be thinking, what is the use of this empty string? You will come to know later on whenever we will be solving problems based on this. Fine. So let's go ahead and see the next definition. The next definition is what we call as a language. Now what exactly is a language? We have already seen in the introduction of this particular video. A language is nothing but defined as a set of strings defined over the given alphabet. We have already seen this. Let's have a look how we write a language. L is nothing but the language. It is equal to a set of X, where this is nothing but the condition. This parallel symbol or this particular symbol over here is nothing but the condition. So L is nothing but a set of X where X ends in BA. The condition is given, X ends in BA over the inputs. It is also called as over the inputs or over the alphabets A, B. So a clear-cut question is given in front of you. L is nothing but X, where X should end in BA over the inputs A, B. The length is not given. The length of the string is not given. It can start with any symbol, but it should end over BA only. Fine. So how to break this entire language into multiple parts? Let's have a look. This language or this definition is nothing but something like this. What happens over here is this particular symbol on the left hand side is nothing but the language. Within the set we are having x is nothing but the string, and following that is the condition where x should end in BA over the alphabets A comma B. Fine. So what could be the examples for this? Example could be ABA, AABA, simply BA, because it is starting as well as ending with BA. Question में क्या दिया? Question में ये बोला है कि it should end with BA. So it can start with any symbol. It's not mentioned over there that it has to start with a particular set of symbols. It can start with any symbol, but we have to make sure that it ends over BA. Similarly, it could be BBA, BABA, and so on. Right? So anything of that sort which satisfies this condition is nothing but a language. Now let's move on to the next definition, which is power of an alphabet. Now what exactly is a power? Power is nothing but if sigma is an alphabet, then sigma raised to k is defined as the set of all the strings from the alphabet sigma of length k. It is a very simple kind of definition, just pay attention. If sigma is the alphabet, then what is sigma raised to k? Sigma raised to k is basically the set of all the strings from the alphabet sigma of length k. So if I say sigma raised to 2, what does it mean? It simply means all the set of strings, or we can say set of all the strings from the alphabet sigma of length 2. So in this case, sigma is A comma B. So what will be sigma raised to 2? It's very simple. It is set of AA, AB, BA and BB. I hope this is clear. Similarly, we can reduce sigma raised to 3, sigma raised to 4, whatever we wish. Similarly, we can say that sigma raised to 0 we have already seen in the past. It is nothing but the empty string or epsilon. So with that, I come to the conclusion of this particular video on the basic concepts and definitions of finite automata.